session. Today I'm going to discuss about the algebraic methodology of solving linear programming problem. At any point of time, if you are feeling that you are not comfortable with any step, then you may interrupt me and you can ask me the relevant portion that you are not understanding. Because I'm again repeating that today's topic is a bit difficult and lots of things that you need to know to deal with this simplex algorithm. My last 14 years experience is saying that no student is comfortable with this particular algorithm, simplex algorithm. Although I try my level best to make the students understand, and whenever I solve the problem, they understand, but when their turn come, then they actually fail to do so. So be very sure that you are understanding each and every step. And in my last class, I also told you that simplex or algebraic method is basically applied when we are not comfortable with drawing figures, graphs. If the number of variable is 2, it's okay. We can draw the graph we can draw the graph in a two-dimensional plane and we can solve the problem. But if the number of variable is more than 2, if it is 3, then with some effort we can draw the three-dimensional figure, but it is not usually recommended. And if it is more than 3, then there is no question of drawing the graph at all. But it doesn't mean that if the number of variable increases, then a particular problem solution must stop over there. In a physical system, there may be situations where number of variables are much larger. Then it is not justified that we are sitting quietly, that we do not have any methodology in our hand to deal with those kind of problems. For this reason, simplex algorithm was developed, and it is an algebraic process by which this type of situations are dealt with. But since this method is too complicated, so therefore I have decided not to introduce more than 2 variables in my first problem, in my initial problems. Okay, so a algebraic method which is much more generalized to deal with a problem with any number of variables, it can always easily deal with 2 variable problem. Okay, so a problem which can be solved by graphical, it can also be solved by simplex. So for this reason, I am deciding to play with this particular question, which is a maximization type of LPP. So I'm writing maximize Z, and you listen to me very carefully, pay attention. It is 2x1 plus 3x2, 2 variable problem I'm considering, subject to 2 constraints, x1 plus x2 less than or equal to 1, and 3x1 plus x2 less than or equal to 4, and x1 comma x2 greater than or equal to 0. It's a 2 variable problem, 2 constraints are there. We are going to deal with this particular problem using the simplex algorithm. Okay, now to start with, you must keep in mind that since simplex algorithm is an algebraic process, it will deal with a system of equation. It will not deal with a system of inequation, because you already know that system of equation gives us a concrete solution, but system of inequation gives us kind of region. So we cannot start directly the simplex algorithm over here until and unless we deal with this constraint. We somehow have to make these constraints look like equation, and once we transform these equations, transform these inequations into equations, then only we'll be in a position to deal with the problem by this simplex algorithm. So my first step number 1 is convert the system of inequations into equations, okay. And since this I need to pay much more attention while teaching this particular topic, so I am actually deactivating the I mean you cannot, you're unmuting yourselves, so I'm deactivating that feature. If you want to ask something at any point of time, please raise your hand. I will let you unmute yourself. So this, I was telling that this conversion of system of inequations into equations that we have to deal with. First of all, what is the way of doing this conversion? Okay, so what we do is that, you see, in this particular problem, there are the inequalities that are present. These are less than type of inequalities. Both of these inequalities are less than type of inequalities. Less than or equal to type of inequalities. That means what? That means in both the inequations, your left hand side is smaller than the right hand side, is smaller than your RHS. Now, practically speaking, if you talk about a balance whose one side is smaller than the other side, then what we actually do, practically we add something on the portion which is having less amount of item in it. We make it heavier and we try to balance the system. So you just think of these individual constraints as a kind of balance. Okay, lower side is the left hand side is kind of lighter than the right hand side in both the cases. Okay, so in both the cases, what I'm going to do, I'm going to introduce a new variable into the system. I'm going to thrust a new variable into the system, into the left hand side, to make it balanced to the right hand side. So this is the way, when a particular system of inequation is having less than type of inequality, we add something to the left hand side to make it balanced with the right hand side. So I'm going to introduce a set of variables to the LHS of lesser than type inequality system. Okay, and these variables will be added to the system, Okay, such a variable. Okay, such variables have certain names. I will tell the name, but first of all, let me do what I'm talking about. So I'm going to add a variable x1 with x1 plus x2. I'm going to introduce another variable which is s1. And now I'm practically assuming that once I add s1, now the system is balanced. This is the mathematical rule. And I'm converting the lesser than type inequality into equality. So that is my first job. Second one has to be with the second constraint, we have to do the same kind of thing. So in the second problem, we are going to introduce another variable which is different from S1. We cannot add the same variable in two different constraints. So we can add another variable S2, and we are writing this in a kind of, you see, kind of diagonal manner. Okay, just see, as if showing you that S2 is present in the first equation and S1 is present in the second equation. It helps you to build something out of it. Okay, so we have this. We have converted both the inequations into a kind of equations. Okay, algebraically. Now the variables, this S1 and S2, these variables, special variables, which have been added to do the conversion, they have a special name. The variables that are added are actually called slack variables. Slack variables. Okay, so this is the first step. Now, my constraints on the basis of which my objective function was there. So we need to know what will become of the shape of the objective function right now? My objective function was of maximization type, so maximize z. And originally there were two variables, 2x1 plus 3x2. Now the question is, since I have introduced two more variables into the system, what will be their contribution to the objective function? So you see, this, if you think carefully, and if you can think of my previous day's problem, that where I formulated the LPP, if you carefully observe, this constraints, these coefficients of the variables in the objective function, these are actually called, these coefficients are actually called coefficients of variables in the objective function, are actually called per unit contribution of the variables. Per unit contribution of the variables into the objective functions, into the objective function. If you want to understand what do you mean by this, then you just go through, I'm referring you to go through my previous day's formulation problem. You will understand what we mean by per unit contribution. So in that respect, we can say that the per unit contribution of the x1 variable in the objective function is 2 units, and per unit contribution of x2 variable in the objective function is 3 units. So naturally a question comes, if I'm introducing two new variables into the constraints, that is S1 and S2, what will be their per unit contribution into the objective function? Now, technically speaking, what we do is that we want to set the variables in such a way so that their per unit contribution in the objective function shouldn't affect the objective function. So this can be mathematically done in the following manner. What we need to do is that we will consider S1 with its per unit contribution 0 into the objective function, and S2 will be considered in the objective function with its per unit contribution 0. That means while solving the system, if you get certain values, you know, after all, whether we deal with this problem by graphical or simplex method, we need to find the value of the original variables, that is x1 and x2. Now, if you want to find x1 and x2, what we will do, we are going to substitute the value into the objective function. Now, x1, we do not have any problem with x1 and x2. These are my original variables. But if I forcefully introduce something into the objective function s1 with some non-negative per unit contribution, non-zero per unit contribution. Suppose if I write here some constant multiplied by s1, so my original objective function will change, and we don't want to affect the original objective function. We want to keep it fixed. The only possibility by which this can be done, we multiply the slack variables that has been introduced into the constraint by the factor 0. So that is being done. So ultimately my system is going to reduce to the following form, or you can say it is going to expand to the following form, not reduce actually, that this objective function is subject to the following set of equations, where the number of variable has increased, x1, x2, s1, s2. Previously, here we had only two variables. Now the number of variables have been increased, and this non-negativity constraints need to be taken care of, because in LPP, as I said earlier, in LPP, all the variables are physical variables and they have to be non-negative. Negative variables, the variables with negative values do not have any meaning. They are not actually feasible. We already know from our previous day's knowledge. Now our latest system is this one. So if you want to apply simplex, we want to apply simplex to this particular converted form. We cannot apply simplex to the previous form. So now you are in a position to apply simplex problem to this system of equation. Okay. Now a little bit of mathematics will be required over here, and you can say a little bit of prerequisites is required over here. The prerequisite is that okay, that we will count the number of variables, and number of equations available in the system. Okay. So suppose if I am giving you an equation x plus y equal to say 0, and if I ask you to solve this equation, only this equation is available, what you can do is that you can immediately write that x equal to minus y, or you can write y equal to minus x. You will say that x is dependent on y or y is dependent on x. So what is happening here? Here you see the number of variable is 2, but number of equation is what? If I consider this n to be number of variable, this is 2, and number of equation, which is equal to m, is 1 only. So what is happening in this particular case is that you are subtracting the number of equation from the number of variable. That is, you are calculating n minus m, which is 1. And this means out of these two variables, x and y, only one variable has independent choice. What do you mean by that? Whenever we are writing x equal to minus y, that means x is dependent on y. So whatever value you substitute for y, x will be negative of that. So if you substitute y equal to half, then x equal to minus half. So minus half comma half is a solution to the given system. If you substitute y equal to 1, then your x equal to minus 1. So minus 1 and 1 is a solution to the given system. Now, conversely, if you substitute x, if you consider x to be your independent choice, you can consider x to be 1 and y to be minus 1 consequently, and therefore 1 minus 1 is a solution of the given system. So actually this system has infinitely many solutions. Okay, this methodology, this mathematical theory will be applied in step number 2 to deal with this simplex algorithm. We are going to apply this methodology over here in the step number 2. Someone wants to say something. Okay, tell me.
Sir, can you repeat the maximize portion? Haven't understood that one.
Maximize portion means suppose this was the objective function. Suppose z is your profit. And while formulating the problem, you have identified the function to be 2x1 plus 3x2. Now in graphical method, what we do? We find the values x1 and x2 in such a manner so that when it is substituted in the objective function z, it maximizes the z. It maximizes the profit. Now, we do not have any problem with this particular thing. But S1 and S2, these variables were not actually present in the physical system. These variables were only brought to deal with the system by simplex method. These variables we introduced by ourselves. These variables do not have any physical interpretation. They are not our physical variables, but we have introduced them into the objective function. Now, if I want to, when a variable is introduced into the objective function, it should be associated with its per unit contribution. Just like x1 has per unit contribution 2, x2 has per unit contribution 3. So in a similar manner, S1 must have some per unit contribution and S2 must have some per unit contribution. But if I substitute some non-zero constant as a per unit contribution to these variables, something which is not zero. Say if I write here, say 5 into S1 plus 6 into S2, that means your objective function is getting changed. So your objective function is getting changed. Your objective function was not 2x1 plus 3x2 plus s1 plus s2 kind of thing. Your objective function was actually 2x1 plus 3x2 simply. But mathematically speaking, we need to show the contribution of s1 and s2 without affecting the objective function, which can only be done by multiplying s1 by constant 0 and multiplying s2 by a constant 0. So that's why I have written the new objective function in this particular way. And we can name, this is our new objective function. So we can rename the objective function as a z prime. We cannot consider this objective function to be z. We can rename this as z prime. This was the original objective function. This is the new shape of the objective function, and we are naming it as z prime. Original one was z, and the new one is z prime. Understood? Now this mathematical methodology that I'm described over here as a prerequisite that I'm going to apply, just carefully look into this. Where I'm going to apply this methodology in step number 2. So you take a screenshot of this page. I'm going to describe this in step number 2, that what I'm going to deal with the system now. This is page number 1. Page number 2. Yes.
So why we can use S1 and S2? Basically, what is the function S1 and S2?
Function is to make these inequalities equality. That is the function. That is the simple thing that I'm going to do. If you talk about if you consider this system to be this system is definitely a disbalanced system, and therefore it needs to be balanced. So how can you bring the equality symbol over here? There is a provision of getting equality over here, but how can you bring the equality symbol? If you add something on the left hand side, you will assume that by adding that amount of item to the left hand side can become equal to the right hand side. But what is the value of that item that I don't know, that I'm going to find? Okay, unmute yourself, Sumanto.
But sir, in previous class, where we can same function in minimize function, where we can where we can there's inequality function that we can not use S1 and S2.
Because that was a graphical solution that I applied in the last class. Graphically, it is possible to draw straight lines and the corresponding region. We don't have to. We were to deal with the regions. Now we are not going to deal with the regions. We are going to deal with something related to the system of equation. So that's why we didn't need actually this kind of thing in the previous algorithm. We could identify the regions over there, because inequations give us regions, but equations give us a concrete solution. So in equations, since algebraic method deals with equations, we have to do this kind of technique in this particular method. Upama, what is your problem? Ask. বলো।
সেটা কি যেহেতু সাবজেক্টে দুটো ইকুয়েশন তাই জন্য দুটো স্ল্যাক ভেরিয়েবল?
Since there are only two inequations, so there are two slack variables. If there are three inequations, there will be three slack variables. Okay.
Three slack variables.
Yes,
okay,
yes.
Thank you, sir.
Okay. So you just look at the prerequisite part. In prerequisite part, what I have done, that the same thing I'm going to apply in the step number 2 right now. So your step number 2 says that find number of variables which we denote by n, find number of equations which we denote by m in the system, calculate the quantity n minus m. This figure will give you this particular figure n minus m will give you the number of non-basic variables. These items, n minus m items, will call the non-basic variables, and remaining m items will be called basic variables. Why remaining m item? Because you know that if I add n minus m with m, we get the total number of variables. So if you are calculating n minus m items over here, so remaining item must be equal to m, so that the total is n. Now number of variable. So these n minus m items will be called the non-basic variables, and these m items will be called the basic variables. And not only this, n minus m variables will be given the value 0, and the system will be solved for m equations and n unknowns. Sorry, m unknowns. So I'm going to explain what I'm doing over here. This is 0, remember. Okay, this is 0. So in my system, just look at the system. In your system, just let's get back to the page. Again, I missed one particular. This was my page. This was supposed to be my page 2. I again missed it. Sorry. Let me write it over here. This is not page 2. This is page 2. Okay. I will do something else over here in this page. Don't worry. So you just look at the this particular system of equation. So how many variables are there in this system now? In our system, the number of variable n is 4. x1, x2, s1, s2. 4 variables are there. Number of equation in my system is 2. Only 2 constraints are there. 2 equations are there. So if I want to calculate n minus m variable, that will be 4 minus 2, which is 2. These 2 variables will be called non-basic variables. And you see, if I substitute, okay, let's talk about later on. And if 2 variables are non-basic, so remaining 2 variables are basic variables. Remaining 2 variables are basic variables according to the theory. Remaining 2 variables are basic variables. Okay. So just I have applied the rule over here. And now I'm going to apply this particular scenario. What it is said that this n minus m variables will be given value 0. Now you have to identify which of the variables you are going to consider to be having the 0 value. Now the rule is that do not touch the original variables. Do not put original variables. Okay, if you're putting original variables, if I substitute x1 equal to 0 and x2 equal to 0, that means you are putting origin into the system. So if I put origin into the system, so basically, if you think of the graphical solution, So the profit value will be 0. So it doesn't have any meaning. Okay, so if I put x1 equal to 0 and x2 equal to 0, if I treat out of these 4 variables, if I consider x1 and x2 to be non-basic, and if I put x1 equal to 0 and x2 equal to 0, that means what? That means graphically speaking, we are putting origin into the figure. And if you are putting origin into the figure, origin is the least amount which is present in the positive quadrant. That means your profit is 0. You cannot say that it is the maximized profit. So this is meaningless. So the rule says that if you want to consider the non-basic variables, graphically speaking, so it is according to the graphical method I'm saying that it would be meaningless if I put x1 equal to 0 and x2 equal to 0. But if I substitute the non-basic, if I substitute x1 equal to 0 and x2 equal to 0 in the current system of equation, then we will not be having any problem, because in the current system of equation, technically speaking, we do not have only this variable x1 and x2 in the objective function. Other than this, we have s1 and s2. So initially we will consider the original variable to be the non-basic variables, and we'll start dealing with the new set of variables. And in the simplex algorithm, our objective is to bring back the original variables having some optimum value by eliminating this new set of variables. So our process is something absurd kind of thing. We want to find the values of x1 and x2, which are the original variables. But in the initial stage, we are not going to consider them. We are going to put x1 equal to 0 and x2 equal to 0. We are going to consider them as non-basic. And we'll deal these two variables as our important variables. And gradually, you will see that during the process, somehow we are going to eliminate this s1 and s2 in such a manner. So the simplex algorithm is designed in such a manner, this variable are supposed to vanish from the picture, and x1 and x2, these two variables must retain some sort of values in them so that the objective function is maximized. So I'm going to deal with this. So the basic rule, the convention, here I'm writing the convention, the word convention, that you just start with the non-basic variable and you consider x1 to be 0 and x2 to be 0. And if we substitute these values in the set of equations, set of two equations with two unknowns, just look at the equation. We are going to get s1 is equal to 1 and s2 equals to 4. s1 equals to 1 and s2 equal to 4. And these variables are initially my basic variables. So according to the theorem, the theory says n minus m variables will be given value 0. They are non-basic variables. The remaining system will be solved for m equations and m unknowns, and those m variables will be termed as basic variables. So here, by convention, we are considering x1 and x2 to be non-basic variable. We are substituting them. We are substituting 0 values for them in the equation, and the remaining system are being solved for 2 equations and 2 unknowns. And out of that, we are getting s1 as 1 and s2 as 4, which are basic variables. These are the initial stages that I have shown you here in this first session. In the next session, I'm going to start with the simplex algorithm. So let's wait for the next session to begin.